And now for the last part of our discussion on work and energy. Let's finish up our discussion with a few examples. So consider now the following example. We have sample problem number 1. A 2 kilogram wooden block is placed on a horizontal tabletop. The coefficient of kinetic friction between the block and the tabletop is 0.5. A wire is attached to the wooden block and pulled with a 10 Newton force such that the wire makes an angle of 30 degrees with respect to the horizontal. The block slides along the tabletop for 1 meter. What is the work done by the kinetic friction? And what is the final speed of the block after traveling 1 meter? So the mass of the wooden block is 2 kilograms. Coefficient of kinetic friction is given to be 0.5. The applied force, 10 newtons. And the angle of the applied force is 30 degrees with the horizontal. The block travels 1 meter, so x is equal to 1 meter. The block is simply placed on the tabletop and then pulled with a 10 Newton force, so initial speed is 0. The surface is horizontal from initial case to final case, so initial height and final height are the same. Let's equate that to 0 since the height does not change. We might as well just set the height to 0. We are looking for work done by friction and for the final speed of the wooden block. Now, kinetic friction, we know to be Fk is equal to mu k n. Work done by friction, therefore, work done is equal to integral of F dotted with dx. So, work done by friction is integral of kinetic friction dotted with dx. And we integrate from initial case to final case. So from initial x to final x. From 0 to x is equal to 1 meter. Dot product, Fk magnitude, dx magnitude, times the angle between Fk and dx. Dx is heading in the same direction as the motion. Fk is always opposite in the direction of the motion because it is opposing the motion. So they are opposite in direction, Fk and dx. The angle between them is 180 degrees. So you have integral from 0 to x of Fk dx cosine 180 degrees. 180 cosine of 180 is negative 1. Fk is mu kn, so we have negative integral of mu kn dx. Mu k is constant, n is constant, so we bring them out of the integration. We are only integrating dx, which will give us work done by friction is equal to negative mu k n x. We know mu k, we know x. To be able to calculate the work done by friction, we need to get the normal force magnitude. For that, we need to do force analysis. So the block is placed on a horizontal tabletop. So let this point be the wooden block. It has mass, therefore it has weight vertically downwards. The surface is horizontal, therefore it will produce a vertical normal force N. Let the motion be heading in the positive x direction. Friction will oppose that. So friction, kinetic friction Fk is heading in the negative x direction. And then you have the applied force F, angle 30 degrees with respect to the horizontal. So you have applied force F rather, and angle theta with respect to the horizontal. And since the object started from rest and then it acquired a non-zero velocity, the object is accelerating, the object is speeding up. Therefore, if the motion is positive direction, the acceleration is also heading in the positive x direction. This is an accelerating system. Therefore, we set F net to ma. And F net is summation of all the forces acting on the system. So you have weight plus normal force plus kinetic friction plus applied force F. We are looking for normal force. Therefore, according to the diagram, normal force is vertical, so it's on the y-axis. So we go to the y component. Y component of F net is F net y. Y component of A is horizontal, no y component. Weight is vertical, negative direction. Normal force is vertical, positive direction. So you have minus W plus N. Kinetic friction is horizontal, no y component. F is diagonal. The y component is opposite the angle theta, so we use sine function. And the y component is positive y direction. So you have plus F sine theta. Isolating normal force N, we get N is equal to W minus F sine theta. Weight is F is just mg. So you have mg minus F sine theta. All of these variables, all of these quantities are known. Plotting in the known values, we get the magnitude of the normal force, 14.6 newtons. Knowing the magnitude of the normal force, friction, work done by friction rather, is equal to negative mu knx. Knowing the normal force, we are now able to calculate the work done by friction. We have work done by friction to be negative 7.300 joules. Next, we need to get the final speed of the wooden block. If we use conservation of energy equation, we need to use the equation that has external force because we have friction and applied force F present in the system. So we have initial kinetic energy plus initial gravitational potential energy plus work done by the external forces is equal to final kinetic energy plus final gravitational potential energy. There's only one object to consider here, the wooden block. So only one initial kinetic energy, 1/2 mv initial squared, one initial gravitational potential energy. You have mgh initial. We have two external forces. We have work done by friction and work done by applied force F. And then in the final case, we have one kinetic energy final, 1/2 mv final squared. And then we have one final gravitational potential energy, so mgh final. Initial speed, V initial is 0, so we have 0 initial kinetic energy. H initial is 0, so initial gravitational potential energy is also 0. The same goes for final gravitational potential energy. H final is 0, therefore mgh final is equal to 0. So we are left with work done by friction plus work done by applied force F, integral of F dotted with dx. F is constant, so we bring it out of the integration. We are just integrating dx. We get fx cosine theta. So magnitude of F, magnitude of x times cosine of the angle between F and x. Going back to our diagram, you have F and x is along the x-axis, positive direction. The angle between x and F is angle theta. 30 degrees is equal to 1/2 mv final squared. All of these quantities are known except for v final. So isolating v final, don't forget v final squared. So we need to get the square root to get v final. Plotting in the values, we are able to calculate the final speed of the wooden block to be 1.166 meters per second. So we have work done by friction and the final speed of the wooden block. And now we have sample problem number 2. We have a flower pot falls off a window. So let's say this is the window. The flower pot falls off the window. The window is 1.5 meters from the ground. The flower pot falls off the window and falls to the ground, eventually hitting the ground. What is the speed of the flower pot as it hits the ground? So in terms of initial case to final case, you have initial height hi and final height hf. Let initial height hi be 1.5 meters and let h final be equal to 0. The flower pot simply falls off the window, so initial velocity is 0, initial speed is 0. We are looking for the final speed, the speed at which the flower pot hits the ground. Now, this problem may be solved by using kinematics, free fall motion analysis. It may also be solved using conservation of energy analysis. I leave it up to you to look up the solution for free fall motion. In this example, let's use the conservation of energy analysis. Now, the only source of acceleration, the only influence rather on the motion of the object as it goes from initial case to final case is gravity. And that's already incorporated in our concept of gravitational potential energy. So there's basically no external force acting on the object. So we use the original equation or the classic equation for conservation of energy analysis. You have initial mechanical energy is equal to final mechanical energy. Initial kinetic energy plus initial gravitational potential energy is equal to final kinetic energy plus final gravitational potential energy. There's only one object to consider, the flower pot. So, initial kinetic energy of the flower pot, 1/2 mvi squared. Initial gravitational potential energy of the flower pot, mgh initial. And then, final case, you have the final kinetic energy, 1/2 mvf squared. And final gravitational potential energy, mgh final squared. Common variable m, we can cancel out m, leaving us with 1/2 mvi squared plus 2gh initial plus 1/2 mvf squared plus 2gh final. We know h final to be 0, so gh final is 0. We know v initial is 0, so 1/2 v initial is V initial squared is 0, leaving us with GH initial is equal to 1/2 VF squared. This equation basically tells us that the gravitational potential energy is converted into final kinetic energy of the flower pot. We know G, 9.8 meters per second squared. We know H initial, 1.5 meters. The only unknown is V final. So isolate V final, plot in the known values, and we are able to calculate the final speed to be 5.422 meters per second. And finally, we have sample problem number 3. A 2 horsepower motor pulls a mini elevator up at a constant speed. The elevator has a mass of 10 kilograms and it starts from the ground. What is the height of the elevator after 5 seconds? Now, the 2 horsepower rating of the motor, that's the average power that the motor can produce. So, P average is equal to 2 horsepower. That's equivalent to 1,492 watts. The mass of the elevator is 10 kilograms. The total elapsed time is given to be 5 seconds. The problem tells us that the elevator moves at constant speed. So V is constant, meaning initial speed and final speed are equal. The elevator starts from the ground. So let H initial be 0. We are looking for the final height. H final after 5 seconds have passed. Now, average power is equal to total work done divided by total elapsed time. Isolating work total is equal to P average multiplied by time T. Work total is the total work done by the motor as it pulls the elevator for 5 seconds. So work total is equal to 2P average times time. We know P average, we know time T, we are able to calculate the total work done of the motor, 7,460.0 joules. Moving now to conservation of energy, we have the presence of an external force acting on the object. That's basically the force done by the motor. Total work done by the motor is 7,460.0 joules. So that needs to be taken into account in our energy analysis. So there's only one object whose motion we consider, the elevator. So 1 initial kinetic energy, 1/2 mv squared. mv initial is just equal to v. V final is also equal to v. Constant speed. So 1/2 mv squared. 1 initial gravitational potential energy. So we have mgh initial. And then the external work done is done by the motor. The total work done by the motor is W total. And then for the final case, we have 1 final kinetic energy, 1/2 mv squared, and 1 final gravitational potential energy, mgh final. 1/2 mv squared, 1/2 mv squared, we can cancel out the 1/2 mv squared, leaving us with mgh initial plus work total is equal to mgh final. H initial is equal to 0, so mgh initial is 0. We are left with total work done is equal to mgh final. We are looking for H final, so we isolate H final. H final is total work done divided by mg. All these quantities are known. Work total, we have calculated. M is given. And G is known, 9.8 meters per second squared. So plotting in the known values, we are able to calculate the final height of the elevator, 76.122 meters. And that's it for now. That's it for our discussion on work and energy. So thank you for watching.